Hello Year 12, welcome to our third video here for projectile motion. We're looking at the Cartesian equation today. We're going to take our 6 equations of motion, or quite specifically, we're going to take our 2 equations for displacement. Right, x in terms of t and y in terms of t. We're going to combine those together, that's all I mean, so that I get an equation, and essentially a function of x, y as a function of x. And that's going to be independent of time. It's going to be an equation that describes that parabolic path of the particle. So all we're going to do here is we are going to make t the subject of one of the equations, probably the horizontal displacement. It's much simpler. And then we're going to substitute that into the vertical displacement equation. Rightio? So here we go. Given, right, in very general terms, vertical acceleration equals g. Sometimes it's negative g. I've used g here, and g could be negative 10 or negative 9.8. Whatever it is, in general terms here, my vertical acceleration equals g. The initial speed is v. The angle of inclination is alpha. That means my initial velocities, v cos alpha is my horizontal velocity. V sine alpha is my initial vertical velocity. So my horizontal acceleration is always 0. My horizontal velocity, so we've just described, v cos alpha, and it's constant. And my horizontal displacement is vt cos alpha. We're going to take it as though this is from the origin. Okay, general terms here. Now the same thing with our vertical equations of motion, right? I said y double prime equals g. Vertical acceleration equals g. Might be negative g. We just send g here. And then I integrate that and I get my initial velocity. Well, it's gt plus constant. My initial vertical velocity is v sine alpha. Probably could have shown a bit more working there, but well, you know, there's only so much space here. And integrating that again, my vertical displacement, gt squared over 2 plus vt sine alpha. Okay, plus constant, but we're going to take the origin, we're going to our initial condition to be the origin here. So now I have my 6 equations of motion, and I am going to begin now by, or follow on, by making t the subject of my horizontal displacement. So t is x over v cos alpha. I'm going to substitute that into, oops, oh, gee, I've gone a bit far there, hang on. I'm going to substitute that into my vertical displacement. Right, I'm going to replace the t with x over v cos alpha. Right, a little bit of work there expanding that out. I get gx squared over 2v cos squared alpha plus x tan alpha, because that's sine alpha on cos alpha, and the v's cancel out. Now I guess I could maybe leave it like that sometimes. That would be an option. However, I do have I've got 2 terms there. One of them has a tan alpha. The other has something over cos squared alpha, or sec squared alpha, of course that is. And sec squared, as we saw in the last video, 1 plus tan squared. So I could replace it that way as well. Perhaps I don't necessarily have to, but I'm going to. So I do that, and maybe I could leave it like that. Well, we'll see in our textbook that it does. Alternatively, I might factorize that, take a common factor of x out of there and get this thing here. Why would that be helpful? Well, perhaps if I wanted to find something like the range, right, of this function. Certainly that's the sort of thing we've been doing before. Then I want y to equal 0, and then I've got 2 factors there. I can use the null factor theorem, either x equals 0 or, right, or that other thing equals 0. I'm going to solve that. So that's an option there. Anyway, from that equation there, you have to prove that. You can't perhaps remember that and write that down to help you solve a problem. But you could arrive at that. You could determine that equation there, and it helps us do other things. For example, we worked out we can find, say, the speed and angle of inclination at some point along the path of that projectile, of that particle, by finding, say, the time then, and substituting that in, finding the horizontal and vertical velocity, combining those together to find the magnitude and the angle of inclination. We could do that. But if I differentiate that equation with respect to x, no, we could do that. That's reasonably good. It looks really complicated, but it's not, because keeping in mind alpha, g, and v, right, they're constants. We'd be provided with those things, probably. They're constants, so differentiating, it's just a quadratic, right? It's just some coefficient of x squared and some coefficient of x. So quite straightforward to differentiate. If I differentiated, that would give me, right, the derivative of that would be the velocity at some point there. Right, I could do that. So that's an option that we could use. Yep. Anyway, so sometimes this equation helps. I think perhaps when you see a question that requires you to do this, it's going to say something like, show that y equals some function of x. Right, and you'll have to perform some algebraic manipulation. You can see we've done a few different things there, where we've dealt with 1 over cos squared or sec squared or 1 plus tan squared. And we've factorized some things. There's a variety of ways that we might manipulate that equation. But nonetheless, you'll notice, so they're independent of t now. And from that equation, if I had g, alpha, and v, right, I would have quite a straightforward equation describing y in terms of x. And of course, the path that my particle traces out is a fairly straightforward path. It's just a parabola, okay? A second order polynomial. Anyway, that's all we have here. That's it. That brings us to the end. Any questions, let me know. Otherwise, I will see you in class.